Hi gang, let's try number 11. So the first thing that I did was get on the derivative calculator and get my derivatives. Okay, so that was like the first thing I did. I took the problem from the textbook and then I worked on finding the derivatives, not by hand but with the calculator, because these would actually take quite a while to find. Alright, now the next thing that you want to do, and you want to make sure you do this, is you want to check that the domain. That's really important you do that. So the domain of this, because there's a plus sign here, is all real numbers. Okay, this rational function could have had asymptotes. It does not, but it could have. So you really want to make sure, like, the very first thing that you find is the domain. You want to see if there's any restrictions to the function. All right, there's not, so I'm good. So now I'm going to move down to the first derivative and I'm going to pick up any critical numbers I can. So in the second derivative, remember the critical numbers occur where the first derivative is equal to 0 or where the first derivative is undefined. So make sure you always remember it's those two cases. So the derivative is equal to 0 when the numerator is equal to 0. So the numerator will be equal to 0 when x is 0. The first derivative is undefined when the denominator is equal to 0. And again, that's not possible because you have something squared plus 3. So that won't ever happen. So I only have one critical number. Okay, so now I'm going to go work on that for a moment. I'm going to put arrows on the end of it because the domain is from negative infinity to infinity. I'm going to put the 0 here for the critical number. Alright, and now I'm going to go ahead and test it. So as I test it, I'm going to pick something like -1 here. I'm going to pick something like 1 here. I'm also going to make the observation that the denominator of the derivative is always going to be positive. So I don't actually need to plug into it because it doesn't matter what I plug in. It's always going to be positive. So I'm only going to plug into the numerator. So I'm going to just save like a little brain juice. Okay? So I'll plug the -1 into the numerator. The numerator will be negative. We already know that the denominator is always positive. So a negative over a positive is negative. So this is negative, which means the function is coming down. The function is decreasing on this segment. Okay, then I picked 1. So I'm going to plug 1 into the first derivative. 6 times 1 is positive 6. All I care is that it's positive. You don't need to plug 1 into the bottom. It's always positive. So positive over a positive is positive. So it means that the function greater than 0 is increasing. Okay, so just because when I give you the test, I usually ask for all the little bits. So at this part, I would ask you to write out where the function is increasing or decreasing. So at this point, you would say f of x is increasing from increasing is over here. So from 0 to infinity, and then f of x is decreasing from negative infinity to 0 on this segment. Alright, now you want to do the first derivative test. And that looks at the patterns around the critical number. Okay, so here's the critical number. On the left side, I come down. On the right side of the critical number, I come up. So that's going to create a minimum, a relative minimum. So we have a relative minimum at 0. Make sure you plug that back into the function because we are graphing this. We want the y value. So I'm going to plug it into the original. So make sure you're with me on that. I'm putting it in here. So y equals to 0 squared over 0 squared plus 3, which is 0 over 3, which is 0. All right, that is the lowest point locally on the graph. All right, great. So I've done everything now I can do with the first derivative. I'm going to go back now and start working on the second derivative, which tells me the concavity and inflection points on the graph. All right, so now I'm going in for the critical points. And again, like the critical number, the critical points happen when the second derivative is equal to 0 or when the second derivative is undefined. Okay, same process, different significance. All right, so to find where the derivative is equal to 0, you set the numerator equal to 0. Now we could have factored this. So this is x plus 1, x minus 1. It's the difference of perfect squares, this guy here. All right, so we have two places where the second derivative is 0, at -1 and 1. The 18 doesn't have a variable, it's a constant, so we can't set that equal to 0. All right, so that's the part where the derivative, the second derivative is equal to 0. Now, the second derivative will be undefined when the denominator is equal to 0, but just like in the previous case, that's impossible with the plus sign. All right, so that's it. That's all the critical points you have at 1 and -1. So now I can go and start to investigate the function in terms of the second derivative. So I'm going to make my number line for that. Put arrows at the end because the domain is all real. I put in my -1 and my 1 because those are my critical points. There's no domain restriction, so that's all I see here. All right, so now I'm going to pick numbers around this. So I'm going to go for like -2, some test values, 0 and 2. I'm going to plug this into the second derivative to figure out whether it's positive or negative. All right, now before we do this game again, let's just note that because this is squared plus 3, not the cube part, because this is an x squared plus 3, that's why it's always positive. Okay, because technically if you have a cube, it could be positive or negative, but not on this base, not on this binomial. The base of this binomial is always going to be positive. Now, don't forget when you're doing the signs to count the negative. You could count it as like the -18. All right, so when I write it, the first negative is for the -18, so that's this negative. When I plug in, I'll plug in -2 here, that's negative. And I'll plug in -2 here, that's negative. Okay, so just make sure you understand how I'm writing it. I counted, this is a negative, -2 in here is negative, -2 in here is negative. The bottom is always positive. So 3 negatives make a negative. 3 negatives make a negative, so a negative over positive is negative. So this segment right here is negative, which means this part is going to be concave down. All right, now I'm going to plug 0 in. Again, don't forget to count the first part. This negative counts out the very front, even though we're not plugging in a variable there. All right, 0 in here would make a positive, 0 in here would make a negative. So that's first one's a positive, next one's a negative. We said that the denominator was always positive. So 2 negatives make a positive over a positive, so overall this is positive. So this segment is positive in terms of the second derivative. So it's going to be bending upward, concave up. All right, now let's try 2. So again, the outside's always negative. A 2 in here is positive. A 2 in here is positive. So the outside's negative. And then we said the After that, you're going to get 2 positives over the denominator, which is always positive. So 1 negative, we'll keep it negative over a positive. Negative over a positive is negative. So this is negative. So this segment is concave down. All right, so I did all my investigative work. Now I'm just going to report back now what I found from this segment. So I'm trying to write this out like I would ask on an exam so you can see how to do it. All right, so now I'm going to write where the original function is concave up or concave down, because this is telling us the behavior about the original function. All right, so the original function is concave up on the domain of -1 to 1. The original function is concave down over here between -infinity to -1 and over here from 1 to infinity. All right, that's my concavity. And then on the second derivative, you also want to do any kind of inflection points. All right, so I'm going to look that you guys did the work on this, okay? So inflection points is where it changes concavity. So you go to the critical point and you see if it changes concavity. Okay, it did here because it went from concave down to concave up. Concave down to concave up. So this would be an inflection point at -1. You have to then go back to the original function. The original function, what you started with, and solve that. So let me just plug that in there. So y equals 2, I'm putting in a -1 here, -1 squared over -1 squared plus 3, which is 1 over 1 plus 3, which is 1/4. Okay, so this is 1/4. All right, we also have, around the critical point of 1, we go from concave up to concave down, concave up to concave down. So we also have an inflection point here at 1. And as we can sort of see, because these values are being squared, a positive or a negative will give you a 1 here and a 1 here because it's being squared. So this will also be a value of 1/4 when you plug it in the original. All right, gang, so now you have to put all the information together, because now you're going to draw the graph. And I'm also, as I'm drawing the graph, I have to scale it. So, like, I have to figure out how far zoomed in or zoomed out I am. And when I'm looking at the values of like the relative minimum, which is 0, 0, or the inflection points, the y value is very small. So I want to sort of like zoom in versus zoom out. The values are very small in this. So I'm going to make one like about there. There's no large values here. So I don't want to be zoomed out too far. Otherwise, it's, you know, you want to sort of zoom in so you can see what the picture looks like. It's different seeing New York from space versus like standing, you know, in the city. All right, now I'm going to put up my values. So let me start with, I'm going to put up my relative min. So at 0, 0 is my relative min. My inflection points are at -1 1/4. That's over here. This is a half, so this would be a quarter. Oh, I see that we need to do one more thing here, so I'll get to that in a second. Okay, so this is my inflection point at -1 1/4. This over here will be another inflection point at -1 1/4. So what I try to do to help you guys, if a graph has like a special feature, I try to ask you about it in the question so that you don't miss it. I do realize we all have very busy, crazy lives, and sometimes little details that can actually be important, we can overlook them in a math problem. So what I try to do on a test is sort of make sure you answer what I'm looking for. So on a question like this, I would ask you, as part of the question is to find the horizontal asymptote, because this has a horizontal asymptote. So that can be phrased in terms of pre-calculus or calculus. So in terms of calculus, it would look like the limit as x goes to positive or negative infinity of your function. You guys remember the rule, top heavy over bottom heavy over equal in degree, right? If it's equal in degree, it's the ratio of the leading coefficients. So this rule we did back on test 1. When you're going to infinity on the function, if it's equal in degree, it's a ratio of the coefficients. All right, so when you look this over, whichever way your brain is registering it, it's a limit concept, because since it's equal in degree, it's the ratio of the coefficients. So